Hey there, welcome to the first video in our analysis of algorithm series, part of the complete playlist on data structures and algorithms in Python. Throughout this series, we'll cover all the important topics related to analyzing algorithms, including basics, order of growth, best average and worst cases, big O notation, omega notation, theta notation, analysis of loops and recursion, and space complexity. Understanding the analysis of algorithms is crucial for anyone looking to build software products or succeed in job interviews. It forms the foundational knowledge that helps optimize algorithms for better performance and identify potential bottlenecks. Many people tend to skip this essential topic and jump straight into other topics like arrays, linked list, and trees. However, without a proper understanding of time complexity analysis, you may struggle to write efficient code later on. Remember, there can be multiple solutions to a coding problem, but not all solutions are efficient. Your code should be robust, efficient, and consume fewer resources, and be scalable as the system demand grows. These skills are essential not only during coding interviews, but also when building real-world products. In this video, we will gain a basic understanding of the topic, so let's dive in. Before that, please take a look at this question. We are asked to write down a function that takes this number n as an argument, and this function should return the sum of first n natural numbers. So if the input n is 3, output should be 6, which is 1 plus 2 plus 3. If the input n is 7, output should be 28, which is sum of first 7 natural numbers. Please pause this video and try to write down a function yourself that takes this number n as an argument and returns the sum of first n natural numbers. We are going to see 3 different solutions, and your solution might one of these 3. We will then compare these solutions and discuss which one of these is more efficient. So here are the 3 different solutions, let's say written by 3 different programmers. Programmer A used the direct formula for the sum of first n natural numbers, which is n into n plus 1 by 2. Don't worry if you are not familiar with this. Programmer B wrote a single loop solution. In this, he simply initialized the sum to 0 and adding I 1 by 1 up to n. So see, range function works like this. When you provide x and y as parameters to the range function, it gives you the value from x to y minus 1 and increment those values one by one. So example, say if range is from 4 to 7, it will return the values from 4, 5, 6 and y minus 1, which is 7 minus 1 up to 6. And here is a solution written by the third programmer. In this program, he has simply used 2 loops. One loop is inside another loop, we call this nested loop. So the outer loop will run for n times and the inner loop will run for I times. So in the first iteration, the value of I will be 1. So the inner loop will run for 1 time and it will add 1 to the sum 1 time. So it will be 1. In the second iteration, the value of I will be 2. So the inner loop will run for 2 times. So it will add 1 to the sum 2 times. In second loop, it will be 1 plus 1. Likewise, in the third loop, the value of I will be 3, so it will add 1 to the sum 3 times. So it will simply give you 1 plus 2 plus 3, which is what you want for n numbers. So this is how this function works. So all of these programs will give you the correct output, but they are written in different ways. Now the question is, which one of these solution is better and takes less time? Well, it depends on many factors. It depends on the machine in which you are running your program. Suppose you are running a very inefficient program in a fast machine, it will take less time. Whereas if you run a very efficient program in an old machine, it will take more time. The second factor is programming language. Here I have written all these programs in Python. Suppose one programmer writes in C language, then the execution of the executable in C programming language file takes less time because there is exe file. In Python, interpretation happens, which is relatively slow. So the time taken of the program depends on the machine in which you are running the program, the programming language you are using, also the background load in your computer. So the program will be run faster in less loaded machine. By just running the program, we can't figure out which program is better written. To overcome this, we have a mathematical solution called asymptotic analysis. In asymptotic analysis, we do not depend upon the machine or programming language in which we are running the program. In fact, we do not have to implement the algorithm or ideas. We can simply write the pseudocode and need not to write the actual working Python code. Asymptotic analysis mainly measures order of growth in terms of input size. If the input size is n, what is the function of order of growth of time taken by the function in terms of input size? Here I have written expressions for order of growth of given three functions. Let's look at the first function. The function performs one multiplication, one addition and one division. For any value of n you provide, be it 1, 2, 100, 1000, it has fixed number of operations. It is not doing anything n times, right? Or n by 2 times or log n times. It is performing single time. So we say the first function as constant order of growth. We write it C1. C1 is any constant and its value depends on the speed of the machine and programming language used. Now let's look at function B. Here the function has fixed number of operations like initialization of sum to 0, returning of sum, and also it has a loop running that goes from 1 to n. The expression sum equals to sum plus 1 inside the loop will run for n times. So we say that this function is dependent upon n. So the larger the value of n, the more number of times sum equals to sum plus 1 will be executed. So we can write the function of order of growth of function B as C2n plus C3. C2n for the loop that will run for n times, and C3 for the fixed number of operations whose value doesn't depend upon n. It is a linear function. It will take more time for larger value of n like 1000 and less time for smaller value of n like 10. I will demonstrate this in Jupyter Notebook in a minute. Now let's see the third function. The third function contains a nested loop. Let's look at this expression sum equals to sum plus 1. How many times is it running? We know that a for loop runs for n times, right? The outer loop will run for n times, and for every iteration of outer loop, the inner loop will also run from n times. So it is n into n equals to n square. A loop can run for 1 time or 100 times, but for both cases, we say a loop run for n times in asymptotic analysis. Let's say the multiplier of this is C4 n square. And this C4 depends upon the machine and programming language as I said earlier. Now let's assume there is some expression before the inner for loop. Here, like print high. How many times it will be printed? It will be printed n times because it lies in outer for loop which runs for n times. So it is of linear time n, and the multiplier let's say is C5n, which is for expression inside the outer for loop. Terms inside inner for loop run for n square times, and the terms inside outer for loop but not inside inner for loop will run for n times. And there are some constant operations as well, like initialization of sum, returning of sum, which we write C6. So this is the expression for order of growth of third function C. During analysis of algorithm, we mostly consider the term with the highest degree or the highest power, because the term with the lower degrees have insignificant effect in the function expression as the value of n increases. For example, let's compare n and n square. Let's say function 1 equals to n and function 2 equals to n square. So let this be n and this be the function value t. So this is function 1. When the value of n is 1, function 1 is 1. When the value of n is 1000, function 1 is 1000. Let's see function 2. It is quadratic. When the value of 1, function 2 is 1. When the value of n is 2, function 1's value is n square, which is 4. When it is 1000, it is fun 2 equals to 1000 into 1000, which is 10 to the power 6. Whereas function 1 is just 1000. So 1000 is insignificant compared to 1 million. So we mostly take the term with the highest power. Now let's see our code in action. Here I am using Deep Note for the coding. It is like the web-based version of Jupyter Notebook. I've also put the link on how to install Jupyter Notebook in the I button above. Now let's assign a smaller value to n. Let's say 1000, and see how much time each function is taking to print the sum. So print function a n. This executed instantly. Now let's see other function as well. Function b and function C. All these functions run instantly. Now let's give a very high value of n. Let's say 1 million. Now let's see function how much time function A takes. Function A ran instantly. Function B took some few seconds, but few milliseconds, and function C, it is taking significantly large amount of time because its order of growth is n into n. It is taking a long. I will stop this. I will delete this for now. Now let's give a even higher value of n. Let's say 20 and see how much time function A and B are taking. Function C will take a lot of time. We will have to wait a lot. Let's see function A and B, how much time they are taking. Function A ran instantly. Function B also took a lot of time here. Now let's give a very high value of n and see how much time function A is taking. Even if in this value, function A ran instantly because it has constant order of growth. It is just performing one multiplication, one division and one addition for any value of n. In case of function B, it is running n operations for the value of n. But function C is performing n into n squared operations, which is very high, so it will take a lot of time. So we have got expressions for values of fun A and fun B, which are order of growth for both the functions. Before we talk about this graph, there are few things I would like to clarify. When we talk about analysis of algorithm, we always talk about sizes of input that are larger than or equals to 0. And also the time taken by the function should always be greater than 0. Because input size or the time taken can never be negative. So we always talk about this first quadrant of this 2D coordinate system while doing time complexity analysis. Here I have drawn graphs for both fun A and fun B. Say fun A is a function that you implemented and ran on your machine, and fun B is a function that your friend implemented and ran it on his machine. Now you are running your function probably on a slower machine and in the programming language that takes more time to run, and your friend has implemented his code in a faster machine and in a language that takes relatively less time. Now how do you theoretically prove that your programming is actually faster and will perform better than fun B on certain conditions? To do that, we do this theoretical analysis where we consider the order of growth of both the functions, and we always talk about large values of n tends to infinite. Now let's look at this scenario. Fun A is the function written by you and this is the function written by your friend, and you run your program on a slower machine, so I have written C1 slightly higher than C3. It took 10 instructions on your machine to do that addition, multiplication and division, and let's say it takes 2n plus 5 on your friend's machine, and we get a graph like this. Now if you look at this graph, what happens is after a certain value of n, your friend's machine always starts taking more time. Now how do you find this value of n? So if you look at this point both the programs will take same time, so we just equate these equations. So 2n plus 5 equals to 10. Solving this, we get n equals to 5 by 2 equals to 2.5. So if we take only the integer values, because instruction cannot be in decimals, n equals to n greater than or equals to 3. So when the value of n is 1 or 2, your friend's program will run faster. But after the value of n more than or equals to 3, your program will perform better. Now imagine a situation, your friend brings a faster machine and value of C2 and C3 are reduced to 1 and 1 for each case. And you got an even slower machine and value of C1 becomes 1000 for you. Now this theoretical analysis fails for smaller values of n. But when you talk about values of n when n tends to infinite, there is again going to be a value of n after which your program is going to take less time, even if you are running on a slower machine and he is running on a very fast machine. Let's see this graph. I have used dot here because I wanted to show 1000 here, and this is your program's taken time. It is always going to take 1000 time constant. We are making some assumptions here, like your CPU load is same and no other apps are running for both of your machines. Now friend's graph is going to look something like this with these new modifications. Now if you compare these two, and if you try to find out the value after which your machine is going to take less time, you can find that value. So you want to find a value, so n plus 1 is your friend's time constant and you want it to be greater than your time constant. So when you solve this, n is greater than or equals to 999. Now for the input size 999 and more, your program is going to run faster than your friend's program. Although this value is dependent on the programming language and the machine used, but it is guaranteed that there will always be a certain value however high it is. Why is it guaranteed? How is it mathematically true? We will talk about that in the next video. Same thing happens when you compare that with Fun3. Fun3 is a quadratic graph with n squared term. It will grow like this, which is much faster than Fun1 and Fun2, right? In terms of constant size. The constants in the function C4n square plus C5n plus C6, they also matter, but when you talk about the value when n tends to infinite, they can be ignored. And we are going to do this mathematical analysis in the next video. Thank you for watching this video. Please remember to like and subscribe to my channel. Your support motivates me to create more content like this. I'll see you in the next video where we will dive deeper into the topic.